Hi, everybody. I am Lynn Kaminsky. I am a professor in the physics and astronomy department. This is my 36th year on campus, and I'm very proud to introduce Alex Vasquez, who is beyond a doubt the student that's influenced me the most in all the years that I've taught here. I hope I've had a similarly positive influence on him. I first met Alex when he was 18 years old, and he came to Sonoma State with his mom looking for an astronomy project. And that was the beginning of a wonderful partnership and mentoring relationship with people in my group like Dr. Kevin McLinn, and with my husband, Dr. Garrett Jernigan, who worked with Alex, taught him how to run telescopes, taught him how to build electronics and participate in part of satellite. Alex and I launched rockets together. He was our rising data intern in the summer. Before he came to Sonoma State, he came and joined our EdgeCube project, did a wonderful CAD model, was our first CalBridge scholar, and is about to go off to graduate school at UC Irvine in the physics department. So we're super proud of that. His senior project is going to be about the particle sensor on the IMAP CubeSat. So take it away, Alex.
All right, thank you so much, Lynn. Let me switch to sharing the screen. Share. All right, and go to slide mode. Camera's in the way of that. Hold on. Okay, and present. All right. Hello, everyone. My name is Alex Vasquez, and I will be discussing my work on the particle detector safeguard for the 2U cube satellite designed by IMAP. In a collaboration with Sonoma State University, Howard University, and the University of New Hampshire, IMAP intends to construct a 2U cube satellite for observing behavior in the Earth's atmosphere. The overall goal of the collaboration is to provide students at these 3 universities the opportunity to design, test, and deliver a device benefiting the scientific community. The IMAP cube satellite will observe the phenomena in the Earth's magnetic field. The sun produces a steady stream of solar wind and outflux of high-energy ionized particles radiating out into the solar system and multiple wavelengths of electromagnetic waves. As these waves and particles approach the Earth, they reach its magnetic field, pictured on the left, and begin to travel along its magnetic field lines. They are then either deflected around the Earth and sent further out into the solar system, or spend some time between the multiple bands of that magnetic field. Symmetrical about the Earth's magnetic axis are the Van Allen belts, pictured in the bottom right. Regions representing where the magnetic field around the Earth, facing the sun, are weakest. The Earth's magnetic magnetic offset axis is offset from the center of the Earth, resulting in one of the Van Allen belts ending a bit closer to the Earth's surface than the rest of it, about 120 meters above the Atlantic Ocean, a phenomenon known as the South Atlantic Anomaly, pictured in the top right. Another phenomenon which we wish to observe is the cusp, the region between where the bands of the magnetosphere split or meet. And if I can use my annotations to point that out, in the left picture, they are right. It is right here, the polar cusp. This split is where electrons and ions run down the band of the Earth's magnetic field eventually meet, resulting in an aurora event in the ionosphere, about 60 miles up. One of the things we are looking for in our CUBE satellite is to solve why the cusp exists in both day and nighttime, because as you can see, this appears to be a result of sunlight coming in from one direction. We also know that these solar winds produce heat particles in the gas in the atmosphere, and we want to know what the electron temperature is in this region. Now, in order to detect high energy particles in the Van Allen belts and within the cusp and the South Atlantic Anomaly, I'm in the process of constructing a particle detection board, which will warn the satellite of particles which may harm other instruments on the satellite. Let me clear annotations real quick, because those stay between slides. So the board works by use of the below sensor, the SI pin photodiode sensor, which is able to detect high energy particles, both thermal electrons and short wavelength waves. They're going to be placed on a 2U cube satellite as pictured on the right. This is about 10 centimeters on the shortest dimension and 20 centimeters on the longest, and will contain all the instrumentation, power sources, and tools that will be aboard the satellite, which goes beyond my project and goes into other parts of the IMAP collaboration. Next came the construction of the particle sensor, which was quite a feat indeed. Each of the parts, you can see a picture of it under construction in the top left. Each of the parts used was smaller than a grain of rice, which made soldering the whole thing a bit of an ordeal. However, with help of my mentors, we were able to get this sorted, and getting through it became fun even, and being able to solder all the parts down and confirm that everything was in working order. The parts list for documentation is below. And then we move on to testing. As you can see on the left, we have the whole setup listed. In the film canister on the left of the image is our photodiode. That is what will be detecting our particles and cosmic rays in the case of our on-the-ground testing. Also pictured toward the center of the page is our actual sensor. Not our sensor, is our circuit. All components have been soldered, all the components are attached to each other and connected to our supplies and detecting instrumentation. Toward the top, you can see our power supply is set to 60 volts, which is necessary for our 60-volt bias. To the right of that is our oscilloscope, which will be detecting any cosmic rays which come in and affect our sensor, which should be occurring once every 30 minutes by our estimates. Also, in order to power the diode itself, we had to hook up an additional 5-volt power supply, which we didn't necessarily have on hand, so I ended up having to cannibalize the wall socket of my brother's pencil sharpener. I was being completely safe during the process. I did manage to scavenge his surge protector for his music equipment as well, just to make sure I have an off switch and nothing got overloaded. As of right now, testing is still underway. We are working with the oscilloscope and actually working toward getting a different one so we can detect the particle when it comes in. As far as future tests, as I stated before, once we detect the particle, it will appear on the screen of the oscilloscope and will appear as a bump of light going upward, which we will save and record. We also intend to test the circuit by use of a square wave generator. The use of the square wave generator is to generate, as might be obvious, square waves, things that are repeatable and can be observed, which we'll use through this test circuit to essentially simulate our detection of a cosmic ray. As well as discussed, we'll be upgrading our hardware, changing out oscilloscopes for the time being. As far as what we'll be doing in the future for this project, we will be integrating it into the greater IMAP collaboration to work on this satellite. We will be combining this with the U-Star board, which is one of the central brains of the Cube satellite, making sure that now that our circuit is working, we can install it and make a greater circuit that will take up less space and still be able to function on the board. Also pictured in the top right is a balloon. This is a depiction of our hopefully future field testing, in which we'll be putting all of our components onto a flat sat and sending all our components and detectors up into the atmosphere in order to detect any phenomenon and essentially just act as a field test for all of our tools in action. And I am planning on continuing my work for an additional 4 weeks past now, all the way up until I have to leave and go to UC Irvine. However, it has been wonderful being able to work on this project with all of my mentors. I want to thank Dr. Lynn Kaminsky, Dr. Garrett Jernigan, and Dr. Laura Petikolas, all for advising and helping with background research on this project. I want to help John Ondoti and Gary Stouffer for board design and basically helping me learn how these boards work and the background behind them. I want to thank the greater IMAP collaboration for providing a community for me to check in with, keep me on task, make sure I was working on this project and collaborating, getting an idea of what else was going on. It's all been incredibly interesting. And of course, I want to thank NASA's IMAP collaboration project and the grant given to them as a source of funding. Thank you all.
you so much. What we have at, sorry, thank you so much. Great job, Alex. I'm seeing in the comments that I concur. There's silent applause, but there's some real applause here. Let's make sure we take a few questions. I'd be happy for this to be in my role as the MC. It could also be the faculty advisor, or whichever wants to happen. I think we haven't decided that in person. It's a little easier to see how this is going to happen. But why don't I look for raise of hands for any questions for Alex? Andrew has a question. Open your mic, Andrew.
So once the particles have been detected, what then happens on the CubeSat after?
So once the particles are detected by my device, it will relay to the Vasquez Cube satellite. This area is full of high energy particles. You might want to turn off and stay safe for a little while, so our instrumentation is either not damaged, and we also don't want to be gathering inaccurate data and using up valuable cube satellite power at a time where we're not going to be able to gather accurate data.
Thank you.
Of course.
Looking again for any hands raised. Well, that was a lovely talk, and I think we've gotten your question. So we'll move on. Another round of applause for Alex.